Swayam Prabha. Digital India. Educated India.
Welcome to this lecture number 24 in groundwater hydrology, and in today's lecture the topics to be covered are the potential evaluation of groundwater pollution, followed by physical, chemical, biological analysis of groundwater quality, and followed by criteria and measures of groundwater quality. Now, let us go to this potential evaluation of the groundwater pollution. So, whenever we need to evaluate the potential of the groundwater pollution, so this few things are essential there. The first one is the identification of the pollution sources and potential pollutants, potential of these pollutants. So, when we talk of this identification of this pollution sources, whether these these pollution sources, are they coming from the landfill, or are they coming from that is the water supply, or are they coming from, say, some other sources like industrial pollution or municipal, agricultural. So, they need to be taken into consideration. And here, so the pollutants, they may be either physical pollutants, they may be inorganic pollutants, they may be organic pollutants, they may be bacteriological pollutants, or they may be radioactive pollutants. When it comes to the physical pollutants of the groundwater pollution, so here you can say this is the temperature, color, odor, turbidity, etc. So, these are all can be grouped under the physical pollutants. So, next, coming to the inorganic pollutants. So, here we get the this is the heavy metals and various other inorganic there is ions as well as radicals. Coming to this organic pollutants, so here in this organic pollutants we have this carbon, nitrogen, chlorophyll, chemical oxygen demand, phenolic compounds which are known as phenolics, and what are popularly known as MBAS, which stands for methylene blue active substances. So, these are all the categorized under the organic pollutants. Next, we need to account for the bacteriological pollutants, so which include the coliform bacteria, the viruses, the pathogens or pathogenic bacteria, and then lastly the biochemical oxygen demand. So, these all are grouped under the bacteriological pollutants. And last but not the least, so there are what are known as the radioactive pollutants, in which tritium is there, which is an isotope of hydrogen, then radium, strontium, and other radioactive materials. So, here, so we need to identify these sources. These are the in terms of their category, in terms of their origin, whether they are originating from landfill, or whether they are originating from any industrial source, or whether they are originating from municipal source or agricultural source, and accordingly we need to take the future this one. And next, what is required is the assessment of the groundwater usage. So, depending upon the usage of groundwater, we need to estimate the potential of pollutants. Say, for example, when we talk of the groundwater usage, so here we need to consider what are the future locations for pumping as well as extraction, as well as so what are the future locations of say the habitation and so on. So, where there is a possibility of more water demand, and then so there is a possibility of groundwater not meeting the quality standards and causing pollution and so on. And after this, we also need to assess the hydrogeological conditions. So, in this, we need to consider the aquifers, their depth, their aerial extent and other details, as well as their hydraulic conductivity and so on, as well as the natural groundwater recharge and discharge areas, the isobath maps. So, all these the hydrogeological conditions need to be assessed properly, so that we can get a fair estimate of the potential pollutants, the potential evaluation of the groundwater pollution. And last but not the least, so the evaluation of the pollution mechanism. So, whenever there is a pollution taking place, so it takes place through the vadose zone. So, that is the basically the unsaturated zone, and here the properties of the vadose zone, as well as such as the hydraulic conductivity, degree of saturation, as well as the connectivity of aquifers, all these things need to be accounted for in the evaluation of this one. So, once we have the information about all these items, such as the identification of the pollution sources and potential pollutants, assessment of the usage of groundwater, assessment of the hydrogeological conditions, as well as the evaluation of the pollution mechanism. So, then we will be in a position to reasonably make a good estimate of the potential evaluation of groundwater pollution. So, now let us move over to the physical evaluation of groundwater quality, and this is taken from the source of the Johnson division from the year 1965. And here the physical parameters of which constitutes the physical evaluation of groundwater quality include temperature, electric conductivity, then the total suspended solids and the total dissolved solids. And here, so the temperature for the normal groundwater, the temperature ranges from say 10 degrees to 20 degrees Celsius, and of course, it may vary also, because these are just normal ranges and there are always one. And likewise, the electrical conductivity of the normal range of variation of electrical conductivity is from 100 to 1000 millimos per centimeter. And coming to this other parameters, such as the total dissolved solids. So, the normal range varies from 100 to 500 ppm, and of course, in this case, so if there may also be regions where the total dissolved solids concentration may go even below 100 or may go even above 500, depending upon the hydraulic conductivity. And likewise, the total suspended solids concentration also normally varies in the range of say 100 ppm to 500 ppm, and of course, it can also, depending upon the various locations as well as various specific cases, it may even go below 100 or it may even exceed 500. And then, so this turbidity also is one of the parameters. So, in which you can say the normal range of the groundwater turbidity is from 1 to 5, which is very much within the permissible range. And so, likewise, so if the evaluation of all these physical parameters constitute what is known as the physical evaluation of the groundwater quality. Now, we will go to the chemical analysis of this groundwater quality, and here in the chemical analysis of groundwater quality. So, the the parameters which are analyzed, which are to be analyzed, are, that is, the concentration by weight, followed by chemical equivalence, followed by total dissolved solids by electrical conductance, then the hardness. So, these are the chemical analysis, these constitute the chemical analysis of the groundwater. And first let us see the concentration by weight. So, in this concentration by weight, so here, so in this case, this milligram per liter, so this is replaced by parts per million, and this one, so this is the ionic concentration, or sometimes, so it is also expressed in terms of, say, microgram per liter. And this one, and it is said that the milligrams per this milligram per liter, so this milligram per liter is equivalent to say 7,000 milligram per liter of dissolved solids. And next we will come to the chemical equivalence. So, in this, the various ions, the conversion factors for various ions are as under. So, here so this is to determine or say to estimate the chemical equivalence. and here, so this is the source is from hem, and in this the chemical constituent and then the conversion factor once we multiply by this conversion factor, so it will is the equivalent concentration. So, will be in terms of in milli equivalents per liter. Per liter. So, if the concentration, so basically that is concentration in mg per liter multiplied by this conversion factor Cf. So, that is concentration in mg per liter multiplied by this conversion factor Cf. So, multiplied by Cf, which is equal to concentration in milli equivalent per liter. So, this is the equation, and here let us consider some of these, one like say the aluminum ion Al plus 3. So, it has a conversion factor of say 0.11119. Likewise, the ammonium, that is NH4 plus, so it has a concentration of say 0.05544, and among them, so these are for some of the cations, like so some more can be listed here, like that is the barium, so Ba plus 2, so it has a conversion factor of 0.01456. And let us go to some of the cations. So, the chemical constituent, then conversion factor. Like say here this copper. So, copper has a conversion factor of 0.03148. This potassium, say K plus, it has a conversion factor of 0.02557. Now, let us come to some of the anions, and here in this anion, so this bicarbonate, that is HCO3. So, it has a conversion factor of say 0.01639, and then carbonate CO3 minus 2. So, it has a conversion factor of 0.03333. Likewise, this hydroxide, that is OH minus, it has a conversion factor of 0.0 0.0 588. And here among the cations, the highest conversion is factor is for the hydrogen ion. So, for the hydrogen ion, the conversion factor is as high as 0.99209. Likewise, among the cations, the least conversion factor is for iodide. So, that is 0.00788. And then this nitrate NO3 minus, it has a conversion factor of say 0.01613. So, this is regarding the this one, the chemical equivalence. And now we will go to this total dissolved solids. By electrical conductance. So, here this one milli equivalent per liter of cations is equal to 100 micro, that is Siemens. So, this is micro Siemens per centimeter. So, this is the conversion for the total dissolved solids in terms of this electrical conductance. And then lastly, we will come to this is the hardness. So, this hardness, which is abbreviated as HT. So, we can it is expressed as calcium and magnesium hardness, and this HT, which is equal to calcium multiplied by this calcium carbonate plus the magnesium hardness, that is also multiplied by calcium carbonate calcium. And so, if this is equal to say 2.5 the times calcium hardness plus 4.1 times the magnesium hardness. So, that will give the total hardness. And of course, so here say some this one, that is so the classification based on hardness, that is water classification based on hardness is say here this hardness in milligram per liter of CaCO3 and the class are, if the hardness is between 0 and 75 milligram per liter, then it is called a soft water. If it is 75 to 150, it is called moderately hard. So, 150 to 300, it is called hard, and 300 above 300, it is very hard. So, this is how the the water is classified based on the hardness. Next, this coming to this biological analysis of groundwater quality. So, here we know that so there is what is called the MPN, the most probable number, to quantify the microorganisms, and also there is what is called this BOD. So, these are two biochemical oxygen demand. So, these indicate the two of major parameters based on which the biological analysis of groundwater can be done, and so accordingly we can classify the groundwater as it is good or acceptable, or that is requiring treatment, and so on. Now, let us come to the criteria, that is criteria and measures for groundwater quality. So, here we should know that depending upon the purpose for which the groundwater is used, so the criteria of groundwater quality has to be decided. So, and we all know that, so this drinking water, it requires the highest quality of groundwater, highest water quality. So, therefore, this drinking water has most stringent this one. So, that is say drinking water most stringent water quality standards. So, next below this is the irrigation water, that is somewhat less, that is less stringent water quality. Then other purposes, so it may, the water quality standards may even be less, say if it is used for maybe other purposes other than drinking or irrigation. So, wherein, so it is one. So, now let us consider this the drinking water quality. So, the drinking water quality standards. So, here let us list the parameters. Then whether they are desirable, or if it is desirable, let us write it as D, or if it is essential, let us write it as E. Then the unit in which it is the parameter is quantified. Then the World Health Organization standards, WHO standards as per say 1984. Of course, they have been revised sometime in the late 2000, and then this Bureau of Indian Standards, BIS standards. So this is the Bureau of Indian Standards. So this is also 1983. Then this upper limit. So here in this, let me also write this upper limit. So now, firstly, let us consider, that is the AL aluminum. So it is desirable, it is not essential, and the units are milligram per liter, and as per the WHO standards it is 0.2 milligram per liter, and as per the this one, Bureau of Indian Standards, so the minimum is so this is lower limit is 0.03 and upper limit is 0.2. Next is the MBAS, that is methylene blue active substance. Methylene blue active substance. So this is also desirable, and this is unit is mg per liter max, and it does this WHO doesn't have a standard, whereas as per Bureau of Indian Standards it has to, it needs to be within 0.2 and 1. Next is arsenic, which is a toxic substance. Of course, however, that is also in this one, and this is it has also been listed as desirable, and this is mg per liter maximum. So again, this arsenic, even the maximum concentration should not exceed 0.01 milligram per liter, and so here, so this is 0.05 milligram per liter, that is the upper limit. So next is this cadmium, and cadmium is also desirable, mg per liter max, it is 0.003, and here, so this is 0.01. Next, let us, so this is the chromium Cr plus 6, so it is also desirable, and so this is mg per liter, and this chromium needs to be within 0.05, and it is the same as per this one. Next is copper. So this copper is also desirable, and so again the units are same, mg per liter, and it is the maximum is 1 as per World Health Standards. So this is World Health, this is a standard upper limit obviously. And in this, in case of this one, so it has to be, the minimum is 0.05 and maximum is 1.5. Next is this say color, and color is it is essential, and so it is expressed in terms of Hazen units, and it is the upper limit as per WHO standards is 15, and as per the Bureau of Indian Standards it needs to be between 5 and 25. So next is cyanide, that is Cn minus, and this is also a toxic substance that was, however, it is also listed as desirable, and it's this one, cyanide is mg per liter max, and it needs to be within 0.07, and so here as per the Bureau of Indian Standards it has to be within 0.05. So next is the electrical conductivity. That is EC. So this electrical conductivity is essential. It is the unit is, I am sorry, this ds per meter, that is deca Siemens per meter, deci Siemens per meter. Then it is 1600 the upper limit, and as per the Bureau of Indian Standards it needs to be between 800 and 4800. So next we will so these are some of the parameters. So let me list the parameter, then whether it is desirable, that is D, or essential, E, then the unit, then WHO standard upper limit, and Bureau of Indian Standards, that is lower limit, upper limit. So we will go to this hardness as the total hardness as CaCO3 in terms of CaCO3. So this is essential, and it has units of mg per liter, and it has the upper limit as per WHO standards is 500, as per Indian standards, so 300 to 500. And next is iron. So it is essential. So the same mg per liter, 0.3, and here it is in case of Bureau of Indian Standards 0.3 to 1. Next is lead. So this is desirable. So this is mg per liter, 0.05, and here also it is 0.05 as per the upper standards of upper limits of this one. Next is magnesium. It is also desirable. So WHO as per this is also mg per liter, and here it is not given. So whereas as per the Bureau of Indian Standards it is 1983, it is between 30 and 100. And then next we will go to this manganese. It is desirable. So mg per liter max, mg per liter, and so this is 0.4, and in this case, in case of Bureau of Standards, it is 0.1 and 0.3. Next is mercury. It is also considered poisonous, but however it is listed, and here this is mg per liter max, and this one 0.001, and here this is same. Next is this nitrate. So it is essential, then 6.5 to 8.5, mg per liter, 6.5 to 8.5, and here it is 6.5 and then 9.2. Now this sulfate. So this sulfate is desirable, mg per liter. So it is 400 is the upper limit, and then 200 as per this one, 200 to 400. Next is like taste. So taste is essential, and here it is so in this one, so everywhere it is written as it has to be agreeable. Next is this TDS, total dissolved solids. So this is mg per liter max, this is desirable, mg per liter max, and then this has to be upper limit is 1000, and it has, in this case it is 200 to 2000 as per the Bureau of Indian Standards. So these are some of the standards, and now let us discuss the this water quality for agriculture. So here this the classification of poor quality groundwaters for agriculture. So this is a source, it is Gupta et al. That is 1994. So in this classification of poor quality groundwaters, so this is the water quality, then the EC of irrigation water, which can be used for irrigation or agricultural water. So in terms of deca Siemens per meter. Next is this sodium adsorption ratio. that is SAR in terms of irrigation water in terms of mole. Next is this residual alkalinity. So, this residual alkalinity in milli equivalent per liter. So, here say if the water quality has to be good, then this electrical conductivity for irrigation water, it has to be less than 2 decisiemens per meter, and the sodium absorption SAR, sodium adsorption ratio, has to be less than 10 mole, and the residual alkalinity has to be less than 2.5 milli equivalent per liter. So, next is if these saline waters, so they have an electrical conductivity ranging from say 2 to 4, and again the sodium adsorption ratio is less than 10, and this residual alkalinity is again less than 2.5. So, this is marginally saline waters. Next is saline water. So, the saline waters, the electrical conductivity of irrigation water is greater than 4, then this, but however the sodium adsorption ratio is still less than 10, and the residual alkalinity is still less than 2.5. Next is high sodium adsorption ratio and saline waters. In this case, the electrical conductivity is greater than 4, and this one is greater than 10, and this is less than 2.5. So, these are all these three come under saline waters. Now, coming to this alkaline waters, so that is marginally alkaline, for this the electrical conductivity is less than 4, this SAR is less than 10, and this residual alkalinity is say 2.5 to 4. Next is alkaline. So, there for them the electrical conductivity is less than 4, the SAR, sodium adsorption ratio, is less than 10, and residual alkalinity is greater than 4 milli equivalent per liter. And next is highly alkaline. So, all these three come under alkaline water, and again this highly alkaline also, this electrical conductivity is variable, this sodium adsorption ratio is greater than 10, and this is greater than 4. So, like this if the electrical conductivity is less than 2, the sodium adsorption is less than 10, and residual alkalinity is less than 2.5 milli equivalent per liter. So, then that is the ideal, and which can be used for all kinds of this agricultural crops. However, if it is either marginally saline or saline or high sodium alkaline, so in that case we have to, it has, depending upon the crop, we need to use this one. And so this is how regarding the this one, and in the next lecture we will be discussing about the other aspects of groundwater quality. Thank you.